Okay, so thank you for the introduction and thank you for the kind invitation to the Africa conference. Actually, it's really a very nice event and I'm inspired, and for some years long I've been trying to put together such a gathering of Czech people in speech and natural language processing, and so far actually never time, bugs and so on, but this gives me a real incentive to finally do it. So this is a great event, and thanks again for the invitation. So I won't repeat who I am. I just would like to say that this is not my work. That was mainly the work of my colleagues and students. So the major guy that contributed to this effort is Martin Karafiat, who is our ASR guru. Then there is Igor Seke, and there is Mirko Haneman, who is now with RWTH Aachen. There is Franta Gräzel, there is Karel Veselý, we will see lots of material from Karel, and there is Kartik Baskar. He's not shooting bow all the time, he's also doing very decent ASR. So for people that know Czechia but don't know exactly where is Brno, basically the Prague people are saying Brno is the last curve when you take the highway from Prague to Vienna. So that's here. And actually it's still the second biggest city in the Czech Republic, about 400,000 population, and it's home of many universities, of which BUT, and also quite a number of high-tech companies. So just to finish up with Brno, it would be probably known for the Bren machine gun that was licensed from Brno to the British, and of course they cannot pronounce Brno. So they just changed the order of the letters to Bren, but it's Brno. Then it's the MotoGP, and then I hope very soon it will be also the speech recognition that we are doing. And just to finish up with this, if you ever come to visit us, we have a beautiful campus that is a mixture of old 13th century monastery and some new buildings. And we are welcoming students, visitors, people coming just for talks and so on. And the group that is behind, it is this group of approximately 20 people. And this year, actually, we are celebrating our 20th anniversary. It was not all the time big as this. It started actually in '97 as one-man show. That was myself. And then it grew up. So that was for the introduction. Now the real technical introduction. Actually, I will be speaking about automatic speech recognition. If you guys are not exactly from the domain, you would also hear sometimes transcription, speech to text, S2T. That's all the same thing. Basically, the point is to take audio and to get to obtain text at the output. And usually this is the scheme of the classical ASR or automatic speech recognition system. We have three main components that we need to train. There's the acoustic models, there's the language model, there's the pronunciation dictionary. The whole thing usually gets compiled into what we call a recognition network. And then in order to make it work from the waveform, we need to compute some features, evaluate the likelihoods, the scores, and then run the search or the Viterbi decoding, which is a huge graph search in this case, to get either the text, that's most of the time in the applications, but sometimes we also need to get some richer representation, and we would call it the recognition lattice at the end. Okay, so this talk will be mainly about acoustic modeling and about feature extraction. And that's the outline. So first I will basically deal with the history a little bit, and in some points it would be quite complementary and maybe even the same as Andreas's talk in the morning. So I would like to speak about NNs used for feature extraction, then NNs for acoustic modeling. Then actually the major part of this talk would be about Babel. Babel was a US project dealing with these low resource languages. And I will mention quite some things that have worked for us in Babel. Then I will just mention briefly two other things that we are working on nowadays, currently, and then will be the conclusion. So let's start with the neural networks used as feature extractors. Well, in the old days of speech recognition, the feature extraction was done with these like signal processing based coefficients, maybe a little bit inspired by the human hearing. So the classical scheme for feature extraction would be MFCC, smell frequency, Kapstel coefficients. Now, around the year 2000, people, and they were clustered around the group of Hynek-Hermansky, that was at the time at OGI in the US, came up with what was called the posterior features or trap-based feature extraction. And that was basically based on the statement that the best features for any classification or recognition task should be as close as possible to the posteriors of the target. If you get such a features, then in the optimal case, you just draw a line, do a linear classifier, and you're there. So the other thing that was found quite important was the long temporal context. And so already in 2000, Hynek, together with Dan Ellis and Sangeeta Sharma, came up with this trap feature extraction, where basically we took the spectral temporal plane. So the spectrum is divided into some critical bands. There were some long patches of energy in each of the filter bank outputs. And there were some little neural nets that we called band classifiers that would classify such long temporal patterns into phoneme classes. And there was a merger that was putting all this together. At the end of the merger, we had again some class probabilities, and these were used for performing the recognition with a standard GMM Gaussian mixture model, HMM hidden Markov model system. So that was around 2000, and myself and lots of people from my lab transitioned through Hynek's lab in the US. And actually, we were quite interested into this, and that was also the origin of the famous BUT phoneme recognizer that we made freely available in 2004. This is basically using the same paradigm of the long temporal trajectories that are classified into phoneme classes. And people were quite happy with this. At the time, it was the best performing phone recognizer around, and people used it for different tasks like speech recognition, language ID, and so on, and so on. So if we were like the commercial people, we would say we have received thousands of these thankful letters. So in this case, it was emails or other reactions, but really we were happy with it, and the people around as well. Then we came up with another thing. So this is a bottle of beer that is brewed in Brno, by the way. But the bottleneck doesn't mean that we should drink it fast or something like that. But it means a structure of a neural net that has a thin layer somewhere in between. And actually, we found out that if we train such a neural net to classify any targets, it can be like phonemes or phoneme states and so on, and then take the information from this thin layer inside. They are actually quite nice and very informative features for speech recognition. And for a long time, it was sort of academic exercise, and we were not sure if this is useful at all. But it was in 2007 when Franta Gräsel has shown that these features are performing actually better than the classical MFCCs. If you combine them with MFCCs, the performance got even better, and people started to be interested in them. So then we made this bottleneck feature extraction a little bit more complicated, and we created what is called SBN, or stacked bottleneck architecture. That's basically a hierarchical structure where we have the first stage neural networks that performs this bottleneck feature extraction. Then the bottlenecks are put together to form even longer temporal context. And there is a second stage net that again contains a bottleneck layer. And this is the final features for the speech recognizer. So SBNs were and still are our and also others' production features. It's very nice that in addition to filter bank energies, they are able to digest and process very nicely other kinds of features at the input. So we have played a lot with the fundamental frequency features that we need, for example, for Asian languages. It's good that with the SBNs, F0 features are helping, and they are not destroying the results for Western languages. They do very nicely in multilingual training, so that's what I will be speaking in a minute. And for some years, that were really the top features that we based our systems on, and that we managed to publicize, and people around were happy to use them well. Until the time, maybe 2 years back, with the emergence of recurrent neural nets, these features started to lose ground. And you will see that for the moment, if you take an LSTM, we can actually throw these features into the dustbin and just make a powerful LSTM, and it works even better. But we will come to this. So there is another component, and that's the NNs used as acoustic model. So that's basically this block, and now I will be really overlapping largely with Andreas. So shout on me if it is too boring. I can speed up. This is just to mention that by maybe 2005, the neural nets were not very popular for acoustic modeling, and they will still largely outperformed by Gaussian mixture model systems. The question is why, of course. So the first answer is that GMMs had lots of tricks of speaker environment adaptation. All these kind of transforms like MLLR, MAP, etc. were developed and tuned for GMMs. The second point was technological or practical. GMMs actually were very nice to train in parallel. So when you look at the formulas for re-estimation of GMMs, there is basically a collection of statistics that can be done in parallel on many machines, and then you can just send these stats to one machine to put them together, and that was it. GPUs at this time were still used by gaming fans, so that was the Quake or maybe something like that in this period, not really scientific computations. And then actually there was really general aversion towards neural nets. Also, actually, the book by Hervé Bourlard and Nelson Morgan was around since '94. People just were reluctant to use neural nets. So around that time, we were on the neural net-based features, but the classifier, the ASR system itself, was still GMM-based. And that was the era of 3 European projects. So the first one was M4, then AMI, then AMIDA, and actually Andreas and ICSI were part of it, where we developed systems for recognition of meeting speech. And sometimes these systems were really complex. So for example, one of the best systems was working in 6 different recognition passes. And there was some mutual, let's say, fertilization or augmentation of the system with different architectures. And I remember sitting once with Martin Karafiat and just asking him what he did, and because we needed to formalize it for the paper. we ended up with like full A3 paper full of building blocks with different arrows like statistics here and alignments there, and then I took another 2 hours to redraw it like in some drawing software. So it was nice era, but very complex systems, and in some way it was quite terrible. So then DNNs took the field. Well, I think you all witnessed this. Why? Of course, there was huge DNN development, more layers, people came up with efficient pre-training of the whole thing. Lots of work done in computer vision. So I think whether it is pre-training or CNNs, the speech guys were always taking the good things from what the vision guys were doing. Massive computing power. Now you can get Tesla GPU for reasonable price, have it at home. And actually the GMMs still had advantages. So they were more easy to adapt, and they performed better in the adaptation, but basically the sheer accuracy of DNNs was so good that it was overcoming the GMMs. Now, of course, for us, the question was whether with the DNN era, our beautiful features would be still working fine. So we first thought that DNNs would make these neural network features obsolete, and that they would be happy just with MFCCs or something very simple. And that was actually not the case. So we found out in these years that by having these complicated stacked bottleneck neural network based features was still better than just pouring plain MFCCs. One can ask why was that? We think that was just because we really took into account the large temporal context, and we were playing with this. So now we are actually somewhere in the year 2012, 13, 14. It's somewhere in the middle of the Babel project, as we will see shortly. Then the recurrent neural nets took over. Also, they were known already from the 60s. Let's say around 2010, 2011, 2012, there were like first successful attempts to get them into speech recognition. First, they were successfully used for language modeling, and then others came. So that was the Alex Graves basic paper that people make them working for speech recognition. And then that was a threat for stacked bottleneck features, because actually we did some experiments with the DNN with these very complex features with the stacked bottleneck architecture, and a bidirectional LSTM recurrent neural network with just a plain filter back energies at the beginning. And we have seen that basically LSTMs with these simple features are working better. So that was the case. First, you have this time frequency plane. Before, we were doing all this complicated processing that was necessary to be trained on many languages and so on. And now the outcome is that if you take a good BLSTM system, you can be happy just by one vector of filter bank energies every 10 milliseconds. Now, of course, we can ask ourselves why is that? That's the answer is quite simple. LSTMs already do work very nicely with the contextual information. And actually, as with many of the learned architectures, it's probably better if the nets decide themselves how to use the neurons and how to use the information, than if we try to enforce our ideas about context and bottlenecks and so on to them. So that was about the acoustic modeling. Now let's come to Babel. So Babel actually is a program, or was a program run by US government from 2012 to 2016, and we were proud to be the part of the consortium that was headed by Raytheon BBN, by the group of John McCool. And the point was to simulate operational scenario of US government, where basically there is a crisis in a country. Of course, the US guys might send some intelligence there, or troops, or stuff like this. And actually, in a short period and with limited resources, they need something to do speech data mining. So the Babel program simulated just this scenario. And during the 4 years, we were actually confronted with many strange languages. And the training data was ranging from 75 hours, that was the good case. That's what they called the full language pack, until limited language pack, that was 10 hours, to very limited language pack, just 3 hours of data per language. And in some scenarios, they simulated the case that we get some little amount of transcribed data, so for example 10 hours, but then we have huge amount of non-transcribed data, which would correspond like to the scenario of tapping some conversation and being able to transcribe just part of them in a limited amount of time. So here, just to calibrate you a little bit to what we were expected to do, this is an extract of nice conversational US English speech.
And then they have 1 week to return their keyword results. And you might ask, well, why 1 week? But there are a lot of research evaluation methods that people are trying out with keyword search, so it is important to leave a sufficient amount of time there as well.
So that's Mary Harper, that was actually the program manager for Babel, speaking at the conference in Olomouc in 2013. And well, your estimate of the word error rate, how much do you think we are getting here? 6% would be very nice for dictation. It's actually worse than that. We are about below 20%. So that's example of conversational speech, but language with lots of resources. And now we have something like that. Now put the volume a little bit lower. It's actually quite.
Kade sangifunela uthambile manje sangazi kade ekhuluma nomunye ubhuti akamasipala ukuthi nekuthi kunabantu ke baphelele umsebenzi.
Okay, so that's Zulu. Your estimate of the word error rate. Okay, so basically, if we are lucky, if we can get lower than 50%, we were the good and well-performing guys, and still actually a little bit less than 50%. It's still leading to something usable. So you see that there is quite a difference between the well-represented languages and the low-resource ones. And some problems that we were faced in Babel was these unknown languages. So of course, no one in the lab spoke them. And sometimes we had to look up the Wikipedia where the language actually is spoken because we had no idea. No linguist phonetician around. And of course, not much data and not fully transcribed data. And these were the 2 main problems that we were addressing during our work in Babel. So the first solution was what I call the multilinguality. It's also trained multilingual training, multilingual pre-training, multilingual system porting, however you call it. The point is that we have a language or a couple of languages for which we have resources, and we are able to train good ASR systems on these. And then there is a data that comes from a low resource language, and we want to combine the know-how that we are getting from these languages with just this minimum amount of data from the new language to come up with a reasonable ASR system. Not perfect, but reasonable. Now, many people have worked in this direction. And we have tried all the tricks that were tried before. So we tried to do some universal phoneme sets. Then, of course, we tried to do some phonetic linking from one language to another based on the IPA tables. But what we found out worked the best for us was, again, let the DNN architectures decide themselves how they want to do the multilingual training. So the thing is that we have a neural net. For the known languages, we always define a part of the output layer that is active for training this particular language. Then when the new language comes, we would discard this final layer and just define a new one. We would first train just this new part of the final layer, and then fine-tune or retrain the whole net with a little bit lower learning rate. So if you want to see the details of this procedure, that's described in Karel's 2012 paper. And actually, I think it's quite an important one, because as we will see, this form of multilingual training works not only for features, but also for the whole acoustic models. Okay, so first we tried it with the stacked bottleneck features, and it was tested on three Babel languages. So the first one was Javanese, then Pashto, then Amharic, and actually we found out that if we train the system just on the target language itself, we get some error rate. And when we used this multilingual pre-training and we were adding languages that the neural net has seen during the pre-training, the accuracy or the word error rate got lower. So we were getting better results. And actually by adding 5 or 11 or 17 or the full bunch of 24 Babel languages, we were getting significantly lower error rates. Because you just should remember that in IARPA we were really fighting for every % decrease of WER. Then what we also tried was to add some other non-Babel resources. So we added some Levantine Arabic, some Fisher, some Mandarin, some Spanish, and we found out to our surprise that the results were not much better. Also, the amounts of data for these languages were actually significantly bigger than for the Babel ones. Now, that's still a very Babel-specific scenario where we have lots of languages to pre-train on. This is not normal case for the normal guys, because usually you would have just data maybe for US English or for modern standard Arabic, and you would like to use this as a seed for some other language. So we also tried this. It was Franta Gräsel who tried to pre-train the system on one big language only, that was the US Fisher database, and then ported it to several languages. Actually, there are two places in the SBN hierarchy where this can be done. It can be the first net, it can be the second net, it can be both of them. We can also play around the layer that gets retrained in these different scenarios. And actually, it was tested still with the GMM HMM system as the backend. And the results were quite encouraging. So the best we obtained when we actually modified both of these layers, and then the second, both of these networks, and the second one had a slightly modified structure, so there was no hidden layer between the bottleneck and the output layer, and we actually saw consistent improvements of the word error rate. To be frank, actually, these improvements are not as good as when we use the multilingual pre-training or many languages. We are still getting something worse. But it's a very practical scenario because you don't need to have 24 languages to pre-train. It's just enough to have one of them. So that was the feature part. And then we tried to do multilingual retraining also for the very best performing bidirectional LSTM models. And one might ask, how did we do it? Well, BLSTM has an output layer too, and we can apply exactly the same tricks, like split first the output layer for individual languages, and then scrap it and replace it with a new one. And actually, when we compared it to the architecture, to the same architecture that was trained just on one single language, we still were seeing consistent improvements. So on all languages that we were testing on, there was a clear improvement. You might think that 1% or 0.8% is not much, but again, I repeat that in Babel we were fighting like fiercely for each fraction of percent. Now, in more detail, how this was done. So first came the multilingual pre-training. The DNN was trained in Karel's fashion with the split output layer into language-specific parts. And the funny thing is that in this case we use just monophone output. Well, it would be nice to use triphones, so triphone stays, but then basically this combined output layer would just be too big. So monophone outputs. And then the adaptation was done, as I told you. We stripped the final layer, we replaced it with the new one for the target language. This one with tight state triphones, so with the detailed phonetic information, random initialization. Then only the connections to this last layer were trained. And then the whole thing was fine-tuned, or the guys also sometimes say settled to the target language by retraining the whole network with some slower and smaller training rate. So that worked. And let me just conclude for this multilingual training. So we have seen consistently better results both for features and acoustic models. It works also with modern RNN-based models such as BLSTMs, especially for low amounts of data, and we think that the multilingual pre-training or seeding just provides this necessary background knowledge on how we people speak, and then these models are just a little bit shifted towards the target language. The important thing is the multilingual training of the BLSTMs does not require any of these fancy features that we were working on before, and you can just take plain filter bank outputs and run, and it provides very decent results. So this is greatly simplifying the whole system. We also saw that the language variety is more important than the sheer amounts of data. So when we actually pre-trained on 24 Babel languages, and then added these big languages with lots of data, we didn't see much improvement, which is again supporting our claim that it's learning some sort of background information on how we people speak. And finally, we can apply this trick also with one big language for the seeding of the system, and then only tuning to the target one. However, one needs to be more careful, and we need more experimentation here on whether this will work fine. So some to-dos in the multilingual training. One big language as the seed. We should verify whether this helps also with LSTMs, because so far it was only the feature extraction work plus this old GMM-HMM system. We are also on reversing the scenario. So so far we were targeting the low resource languages. But with having all this Babel data, we can take all the low resource languages, many of them, and try it on big language, just on US English. And that's what Martin is working on now, and it seems that it helps. And Martin should write an ASRU paper, so hopefully, or thanks God the deadline was shifted, and hopefully his boat in Poland, where he is now sailing, will not sink, and he will be able to finish this paper. And then, of course, we need to make this thing practically available. So it would be nice to have Kaldi recipe for general public. And also we are on this in a project that is sponsored by European Commission, where Phonexia, our partner, is the leader. We basically need to shift this into production mode. So that was for the multilingual. Now the next things will be described more shortly, because the second possibility we can do is this semi-supervised training. And there will be in this afternoon a seminar on unsupervised training. I'm looking forward to it. So how we understand it is that there is some transcribed data that has transcriptions, a lot more of non-transcribed data, and the system is classical. We train a seed system on this blue portion of the data. We recognize this orange portion, then we determine what is good, and we select it for training. We retrain on the whole thing, and then just to be sure that we didn't screw up too much, we retune on the transcribed set. So just a question to the public, which of the points you think is the most complicated? Of course, yeah. So determining what is good in the automatically transcribed data is the most problematic thing, and that's something where Karel Vesely was very active. So we need some confidences. These confidences were computed out of the recognition graphs or lattices, and now you might ask what is the good granularity to determine the units to add or remove from your semi-supervised training. It can be the whole sentences, it can be words, it can be just frames. So he has done quite some experimentation in this, and the outcome is that words perform the best. Another thing is that based on the confidences, we can either take or not take the data into the training, or we can weight it. We can make it probabilistic. So also the probabilistic approach provided a little bit better results. Actually, we are mostly sticking with the word selection because it's more practical, and we do not need to tune any additional thresholds or hyperparameters. Now, the question is, once we have these confidences computed and we have settled with the word selection as the preferred technique, is how much data should we take? And here Karel has run quite an extensive experimentation and has found something that we are calling Karel's magic. On Babel Vietnamese, the accuracy of the seeding system on some little development data was 40%, and the optimum amount of data to take was 40%. On Babel Bengali, 37, 40%. Then he said, okay, this looks weird, so let's try it on some other data where we are completely elsewhere in the dynamic range. US switchboard, 73% accuracy, 70% data to be taken. So this Karel magic means that if you want to have a good amount of data to take, you just measure the word accuracy on the little development set, and you take exactly this amount of data, and it works. So conclusions for the supervised. Word selection works well, is practical, doesn't require any other hyperparameter tuning. You should reserve a small depth set within your transcribed data, then train the seed system, recognize the non-transcribed thing, measure word accuracy on the dev data, and take exactly this amount of words with the highest confidence, and it should work for you. And then, of course, you should not forget to retune the system on manually transcribed data. There is a paper that Karel will have at Interspeech in Stockholm, and hopefully he will finally finish his thesis. So there will be more details in this document. Solution 3, speaker adaptation, speaker and environment adaptation. Basically, in the past, as everyone, we were playing with many techniques such as CMLLR that can operate on features. But then, when switching to neural nets, we were interested in approaches that would basically be more directly related to the networks. So Andreas already mentioned, and we also heard it in Hagai's presentation, that there is the I-vector paradigm as very popular technique for producing low-dimensional vectors characterizing the speakers. And that's actually something that the ASR people have adopted, and nowadays I-vectors are very popular for speaker adaptation. There is another possible technique that was done by us with some cooperation with the people from NTT in Japan, and that's called SSNN. We call it sequence summarizing neural nets, basically defining a little neural network that is doing averaging or summation over time, and that is able to come up with one vector characterizing the utterance just itself with within the DNN paradigm. Now, when we compared these two approaches on Babel, we found out that sometimes I-vector would be better, sometimes this D vector as DNN vector would be better. The combination of these two doesn't work all too much. So the good advice, if you want to do such a type of adaptation, is if you have a good I-vector extractor, or you have people in your lab that are able to build an I-vector system and retrain it for you, then go ahead with I-vectors. You can also take our free implementation that is available at the voicebiometry.org page. And if you want something simpler, that is not as good, but it's nicely nicely embedded in the neural network paradigm, and you won't need to compute any Gaussians and I-vector extractor and so on, then go ahead with the sequence summarizing neural nets. So there are more tricks that I will mention just briefly. Augmenting the data. Again, this is not something that we at BUT have developed. It was known, but we basically augment the training databases with reverberation. You can get the tool from Erlangen guys. We are noising them. So around there is the free sound. There are other sources of free noises, or you can just get out and record something on the street. It will work as well. The funny thing is that there is the cocktail party noise, like other speakers, and this can be very easily obtained just by mixing up other data from the same corpus, maybe 10 speakers, 50 speakers, and it will give you a very nice cocktail party setting. And then, of course, there is lots of data engineering, making different random sets out of this. If you want a versatile system that would work for the original condition and also for the reverberated condition, then you need to use both of them. And for us, this worked very well in IARPA Aspire. So that was a challenge in 2016 where we were quite successful. And it also helps us in Babel, with Babel languages, because for some data of Babel, it's not just telephone, it's also recorded in far field, so we need to do this kind of trick. We are also not agnostic to the standard signal preprocessing tricks. So for example, the WPE, the weighted prediction error, that was developed by NTT guys works very nicely for us. It performs some sort of de-reverberation, and it's just a signal processing based technique without any training. And we also make use of DNN autoencoders to perform de-reverberation and denoising. It's actually something quite simple. You take a block of spectrum, you put it at the beginning of the neural net, you train it in the regression mode just to estimate the clean spectrum in the center. And for the training, we can make versions of the original spectrum just by artificial reverberation and artificial noising. And this is working for us as well. So that was the things that we were and are using. Now maybe something more under construction. The first one is what we call the RMNs, residual memory nets. The thing is that we are getting excellent results as everyone with BLSTMs. But the other thing is that BLSTM is really complex architecture, and what we especially don't like are these recurrent relations. So it's quite difficult and slow to train them. So we have been playing mainly Kartik Bhaskar with a non-recurrent structure that is called RMN. It's actually, it can be compared to a very long FIR, finite impulse response filter. Like many blocks, it looks complex, but there is really no single recurrent connection. And when we were comparing this with LSTMs, actually we got comparable or slightly inferior results, but with much simpler architecture and fast training. And there is Kartik's paper from this year's ICASP from New Orleans with the details. Even more challenging or more exploratory is what I call the ASR from raw data. So this is a dream of speech recognition people. You get lots of audio data from one side, lots of unrelated text data from the other side, but just by tapping some internet resources. And you want to have a speech recognizer coming out. So that's a dream, but only partly a dream, because there were already people working on it, taking Bayesian models with latent parameters, trying to make the link between the acoustic, between the language model and the acoustic model. And what was quite important there was some automatic definition of speech units. And there was the whole work group last year at Johns Hopkins that was led by Lukáš Burget. And there is a number of papers that came from that were consolidated to a report. The report cannot be found anywhere, but as I was helping the guys to edit it and put it together, you can just ask me, and I should push Hopkins guys to put it finally on the web page. So I'm almost at the end. The first thing that we see around, in my point of view, is the democratization of ASR. So 10 years back, ASR was really some weird topic, just few crazy guys that could do it. Now I think it got much better with the general interest of students, of the population in machine learning. People have already seen the commercial applications around, like Alexa, Microsoft things, Google things, and so on. There are toolkits around. So there is Scaldi, there is CNTK that Andreas mentioned in the morning. So normally I don't do publicity for Microsoft, but CNTK is really a great thing, and we are using it all the time, and it's running on Linux. And many of these toolkits are coming with recipes. Data is still a problem, but it's getting better. So there is some data supplied by volunteers. There is public data, and we hope to push one day the EC into production of new generation of speech dots and speak-ons that would be really available to the community, not as the old databases. And finally, the computing power. You can buy for reasonable money a Tesla, and if you can like support the noise and the heat, you can have it running at home, or you can use any of the cloud computing services. Still things to do. Rapid development for new languages, it's not something finished. And there is actually only a fraction of world's languages covered by commercially working ASR. So if we and you in companies want to approach the customer, we should be operating on more languages and also on more dialects. So some languages, like for example Arabic and German, seem to be like languages, but actually it's a bunch of languages. I don't know if I have no experience with Arabic, but if you come to Switzerland and you think it's German, it's not really German. And using the free data that is around is another challenge. Then actually there are all these funny and unexpected channels and acoustic conditions. So there is more interest in mic arrays. Everything gets learned and DNN based. There is lots of work to be done on the interaction with the things that actually we can mine from speech besides ASR, speaker ID, language ID, and other meta information, because everything can help us. And also we should understand that ASR is like not the end of processing, but it's mostly at the beginning. It's enabling technology. So we need to speak to the guys that are using our results, like whether it is translation, dialogue management, and also know what the customers need. So people sometimes asking whether there is time for retirement for speech. Well, rather not. That's the current state, and this is ending my talk. I thank you very much, and I thank you for invitation to Africa.
Hello. You mentioned that part of the challenges in Babel was training new languages or new dialects. And you mentioned US English as being a language with a lot of resources. But for example, if I have a US English and there are these minorities like Spanish, Spanglish, and things like that. So did you try adapting from US English to dialects of US English?
I think it's possible. So basically, if you can get enough data from your target language, domain, dialect, whatever, then you can forget about my presentation, because you just train a good system and that's it. But the problem is that if you have just little data, then you might use one of the techniques that I was speaking about. So for example, seed it on US English. You might try also to seed it on Spanish. There is quite an amount of Spanish corpora. And then like do this multilingual porting to the domain that you are interested in. I think it will need some data. You will have to collect some data if you want to address this particular domain, but it's probably much less than if you collected the data just to train a system from scratch.
Just one more question. Do you have a Kaldi recipes for the RMNs?
For RMNs, I think there is no one. I should ask Kartik, who is working on this, if he has one and if he is willing to share. Generally, we are sharing lots of stuff from BUT. So maybe just drop me an email and I will ask.
Okay, thank you.
Okay. My question relates to the multilingual aspects. Actually, yes. You mentioned the large context that we use when we process speech, and you also mentioned the fact that word-level choice, word-based selection for the unsupervised or semi-supervised. Yeah. I'm trying to combine these two issues. So what I was wondering is whether it still could be language dependent, or could be like the context would be asymmetrical for different languages, or it would depend on, the word level scoring or word level selection would depend on the lengths, the typical lengths of words in a language. I mean, I'm still looking for some asymmetry.
Yeah. I see. I think I'm getting the point. So I think Karel was investigating this correct way of defining the units to select for the semi-supervised training in several languages, and the words came as the best. But the thing is, again, the amounts of data. So actually, I think if you have enough data to throw out, then you just go ahead with sentence level confidences, and in case you spot any single problem in the sentence, you just throw it out. So if you have abundant data, that's probably the approach. But in case your data to pick from is limited, then words seem to be like the good choice. But for more details about the different languages, I need to ask him myself, and I think there are more details in his thesis to come.
Is complementary when you speaking about the magic percentage of the per language, 40%, 70%. Do you think this percentage is concerning to the language or to amount of data per language?
Well, if I remember correctly, he tried it for two Babel languages, then for US English, I think also for a couple of other ones, and it was quite consistent. So the amount of data, actually, when you are evaluating this magic amount of data, you don't care about the amount of unsupervised data you have. You really care about the performance of your seeding system and of its performance on some part of the data that you have. So basically the point is to really judge the quality of your basic ASR system. How can you trust the transcriptions of the unsupervised data? And if basically you find high word accuracy, you see, okay, that's probably good. So then I'm able to safely select more data. If it is less, you really want just the data with the highest confidences. So that's the point.
Okay. And the second question, do try to extend the variation of the data for training using variational autoencoders because you cannot collect different types of noise and other things.
Okay, so we are not doing this with variational autoencoders. We do it just very simple engineering way by simulating the data. We are really like noising it, reverberating it, trying out different room configurations with the reverb tool from Erlangen, putting together different kinds of noises, and then training the system on this. There is the Aspire paper, I think from 2 years back, that contains details of all this. So we are actually very simple guys doing just standard engineering tricks. And there was a question over there in the yes.
Regarding this also supervised portion and a large unsupervised portion. Yes. Have you tried or considered other methods? Because when you select something that already has satisfactory level of confidence, aren't you just sticking to something that you have already trained and practically rejecting something that you should have considered as addition to your database?
That's a good question, and actually, yeah, I agree with you that we are reinforcing the knowledge of that the recognizer might already have, but that's basically what we empirically found that works. So yes, we are doing it this way.
I would like to refer to your last slide when you concluded regarding the availability of language resources to the community. First of all, I fully agree that that would advance everybody, but I got 2 points that I'm not sure that I agree with you. If I recall, it was in the conference you organized that almost that Pedro was on stage and everybody was complaining that Google is collecting huge amounts of data and is not sharing with the community. Do you see in the last years any change of attitude from the large organization that has huge amounts of data sharing with the small companies in the academia? Secondly, at the time, a few years ago, I was part of SpeakOn and Speech.consortiums, And there was a certain point that the European Commission said no more funding for language resources. And you mentioned that you think you may convince them. Is there any change in policy of the European Commission?
Okay, so the answer to the first question is that no, I don't think we have seen much data available. But on the other hand, Microsoft and Google and the likes are private companies, right? So actually they own what they paid for, and if they don't give it to you, then they have right to do it. So what I was speaking about was this data that was created with public money, the speech dots and speak-ons, where the EC has sunk tens of millions of euros, and now we can get it actually for very high prices, and yeah, and few people are buying it, and this data is just getting obsolete. So I know actually the position of the EC. They have some sort of calls in the Horizon 2020 for the data incubators and big data validation strategies and so on. And I was asking whether we might try to put together such a call, such a program to create like massive data for speech. So the answer was not for the current H2020 calls, but that they might consider it in some future calls. So let's hope they will. And if anyone actually can lobby for this and speak to the EC guys, please do.
Thank you very much.
Thank you. Thank you.